Thank you so much for the invitation to share some of the work we do at our laboratory. As Ana said, we work at the National University, Universidad Nacional. I work at the Polymer Science and Technology Laboratory. Those are some of our facilities. Costa Rica is a really small country located in Central America. And we have 5 state universities. Universidad Nacional is one of them. And we work at the chemistry department. This is the building, the new building of chemistry. And we belong to the Faculty of Exact and Natural Sciences. So I'm going to show a little about the work we do in the laboratory with residues. We have 3 main research areas: composite and nanocomposite materials, converging technologies, nano and biotechnologies, and we extract biopolymers like collagen, chitin, chitosan, starch, and cellulose. And we have this main objective of using residues. We use agriculture, different type of agriculture residues. Today I'm going to talk about specifically about pineapple and aquaculture residues, mainly so a skeleton of crustaceans, mainly shrimp. About agriculture residues, as I said, the pineapple case, well, is a big issue in our country because, as you can see, this is a pineapple plantation. It's a really extensive area cultivated with this plant. And Costa Rica is one of the main exporters of pineapple, fresh pineapple worldwide. It represents an important economical activity. The main destination of this pineapple are USA and Europe. And for every fruit that you can get, you leave a complete plant of pineapple in the field. I'm not talking about the crown, it's the full plant that stays in the field. So that means there's a lot of biomass that stays in the field and gives some environmental issues. Per hectare of pineapple cultivation are produced 300 tons of rastrojo, that is the leaves and the stem of the plant. And for 2018, it was more than 40,000 hectares plant. This biomass has a high volume and slow degradation. And the main processes applied are chemical drying and soil incorporation. This is the pineapple rastrojo in the field. The biomass, like I said, is a huge amount. It's mainly composed by cellulose, hemicellulose, and lignin. And the cellulose, I'm not going to talk about cellulose, but for the pineapple leaf fiber, the main component is cellulose. So it becomes an emerging source to obtain cellulose from agricultural residues. We have been extracting micro and nanocellulose and try to find some applications for those materials. Micro and nanocellulose have some properties like high mechanical strength, very absorbing, light, non-toxic. The fibers has a high aspect ratio and elevated surface area and high thermal stability. Some applications we have been exploring are hydrogels, electronics, thinking about electronic paper, filtration system for water purification, films, and composite materials. Those are some pictures from the work we have been doing. For the pineapple leaf extraction, we take the leaves. We usually focus our attention on the leaves, not the stem. And we do mechanical processes that is called decryptication. Then we do like a soaking process, and then we do a bleaching process. And we get this material that looks really similar to cotton. From this material, we extract microcellulose. the microcellulose extraction is made by a controlled acid hydrolysis. So you eliminate the amorphous regions and you keep the crystalline regions. It's not an extensive hydrolysis, it's a mild hydrolysis. So you keep these structures that has these crystalline and these amorphous parts. We have been preparing microcellulose and PLA composite materials. PLA is well-known polymer. It's a aliphatic linear polyester, and is compostable under certain conditions of humidity and temperature, and can be easily consumed by microorganisms. Okay, let me move this. For the microcellulose, we did a thermal analysis. As you can see, the thermal stability increases when you go from the puff to microcellulose. For the infrared analysis, usually we focus on these areas to look if the lignin and the hemicellulose was removed during the first processes. And also we do X-ray diffraction to analyze the crystallinity index. The idea is that when you go from PAF to MCC, the crystallinity index increases. It goes from 35 to 70%. Also, here are some images of the pineapple restaurant or the leaf fiber. As you can see, we have the fibers. There's some porosity because the treatments we applied previously. And then we have the microcellulose. As you can see, these are bundles of microfibers. And here you can see a fiber. Then we prepare this type of composite materials with different amounts of MCC. These materials, I don't know what I'm talking. I'm touching something. Let me see. Okay, I have this window. We applied some pretreatment with terbutanol and polyethylene glycol. Pretreatment increased the nucleation capacity and interfacial interaction, as well as the compatibility. About the thermal analysis, as much MCC is added to the material, the thermal stability increases. And the range of temperature of degradation is between 290 to 400 Celsius degrees. Also, by DSC, it was shown that the melting heat decreases and the crystallinity decreases. And from DMA analysis, the dynamical mechanical analysis, the storage models increases. Also, we did these same images before and after the fracture, applying this mechanical treatment. Before the fracture, you can see the surface, and then you have these images after the fracture where you can see the fibers coming out of the matrix. This implies that maybe the interface between the fiber and the matrix can be improved. In the case of nanocellulose, nanocellulose can be nanofibers, NFC, which maintains the amorphous and the crystalline parts. The diameter is between 2 and 20 nanometers, and the length can exceed 10 micrometers. It's a long fiber. And for the case of NCC, nanocrystal cellulose, by an acid hydrolysis and extensive acid hydrolysis, you can separate the crystalline parts. The diameter is smaller than NFC, 8 to 20 nanometers, and the length can be from 100 to 600. The NFC extraction we applied for the pineapple leaf fiber was mediated by the tempo oxidation first. The tempo oxidation is a specific process to oxidize the hydroxyl groups in carbon-6, and then we apply grinding process with a Masuko grinder and homogenization, and then microfluidization. By this process, you can get this type of hydrogens. And for the NCC, as I said before, the hydrolysis is an extensive hydrolysis. So you get this suspension after dialysis, where you keep the crystalline parts. And as the process is made by sulfuric acid hydrolysis, you get these sulfonate groups on the surface that improves the water dispersion and gives a negative charge in the surface of the fibers. For the characterization, we did AFM, TEM, FTR, and also we analyze size and set the potential for the case of NCC. Those are some AFM images. Also, I put here the size. This is for NFC, and this is for NCC. As you can see, the size of the fiber is different. Here you have length about 1 micrometer and width about 3 to 5 nanometers. For the NCC, the size is about 700 nanometers, and the setup potential is minus 34. Like I said before, has negative charge. Also was applied a SEM analysis, is similar. For the NFC, you can see this network of fibers, and for the NCC, you can see the needle-like small parts. From the thermal analysis, as expected, the thermal stability increases by extracting the NCC. Goes from 355 to 376. That is expected because you keep the crystalline parts and eliminate the amorphous parts. Also, we use this NCC material for starch matrices to make composite materials. This starch is extracted from this bitter cassava that is not used for eating. It's not eatable. And here are some pictures around the optical and SEM images of the starch granules in this variety of these. Here are some images of the materials obtained. Those were characterized also by thermal analysis. The range of thermal decomposition is between 340 and 345. It's a small range. And for mechanical properties, as you can see, as much NCC was at the tensile strength increased, the maximum amount was 15%. And for the elastic modulus has a similar behavior, more NCC, higher elastic modulus, and the higher amount was 15% of NCC. Also for this material was made water solubility analysis, water vapor permeability and transmission, and opacity. Also were applied some antimicrobial activity for some bacteria and some fungi, and it gave interesting results for application in food. Also, we prepared nanocellulose films. Here we applied 2 different methods. One with tempo oxidation as a pretreatment, and then ultra-trurex is an homogenization process, and we get this suspension, And also we apply Mazuko grinder, and you get this pulp is like the paper pulp. And then by microfluidization, you get these hydrogels. We did a process to get these films similar to the process applied for paper. And we got these samples. This is bleach, is quite transparent, and this is unbleached. So it keeps the lignin. The idea was to compare if it is necessary to apply a bleaching process. Also, this depends of the application that we are looking, of course, but the idea is to compare these materials. This process of microfluidization and Mazuko grinding were made in Aalto University in Finland. One of our students went to Finland to do the processes. Here you can see some AFM images. This is for NFC, and this is for the film prepared. I think this is the bleach material. And you can see the network formed by the nanofibers. Finally, I'm going to talk about briefly about aquaculture residues. Mainly, we work with the shrimp shell that becomes a residue in the aquaculture industry because the shrimp is exported without the shell. We apply on first chitin is a polysaccharide really similar to cellulose, and it has 1/3 of minerals, 1/3 of protein, and 1/3 of chitin. This chitin can be extracted by eliminating the minerals by acid treatment, and then protein by alkaline treatment. We get this material, this is chitin, and we have a pilot plant where we do this process. Then the chitin is converted to chitosan by the acetylation process in this reactor. So we modify the structure to get these functional groups, primary amine groups, that makes that chitosan can be soluble in light acid media. That has some advantage. This is our pilot plant. We can process about 300 shells per batch, and the yield is about 20 to 30%. For the case of chitin conversion to chitosan, the yield is about 50 to 60%, and per batch we can process about 5 kilograms. Some application for chitin and chitosan, well, for chitin the applications are less. Mainly have been applied as a nematicide for soil preparation. And also from chitosan, you can make fibers, control release system. This is my chitosan microparticle, chitosan-based emulsions, like flocculant agent for water treatment, because the amine group can be charged positively. Also as a particle stabilizer, for example, for gold nanoparticles, and also for chitosan, you can get these films or three-dimensional structures. For the case of films, can be made by casting. Actually, this is a composite between chitosan and collagen, also extracted in our laboratory. And as you can see, it's a film, a transparent film. Those are some images of the film. And also you can get these three-dimensional structures by lyophilization. And in this case, we studied the release of an antibiotic, thinking that this material can be applied in the skin for burns. Also for chitosan and other applications we have been exploring are the chitosan nanovesicles, and also the chitosan nanovesicles as like a mini reactor to get gold nanoparticles. Here are some images of the anisotropic gold nanoparticles that also can be applied for some applications, for example, as a detector of different substances that have been explored. And also chitosan, you can get this type of beads. Those are beads between chitosan and iron. Those beads were applied to arsenical removal in water. So has a lot of applications. Thank you so much for your attention. I would like to thank to all the institutions that make possible the research that we do in our laboratory. And as a conclusion, I can say that we have this great potential to use residues from agriculture and from aquaculture residues to obtain these materials, renewable materials, to get different applications. Thank you so much.